Hello all. Today I'm going to talk about a blast wave in a one-dimensional coal gas. This I have we have worked with Abhishek, Paul Krapinski, and the former postdoc of ICTS, Subhadeep, who's now in Frederick Alexander University. So the flowchart of the work, basically what we are doing is that we have a macroscopic Hamiltonian system. So for n particles, we'll have 2n equations. Let's say we're talking in one dimension. Then if you want to describe the system, you have to talk about solve the 2n equations. So we try to see whether you can, simplify the description. If instead of 2n equations, you can solve with less number of equations. So that's why you try to look at the emergent behavior in the system, basically. So basically, out of 2n, how small you can get, what are the least number of equations, least number of equations that you can use to solve describe the system. That depends on the number of conserved quantities in the system. Generally, we come across non-integrable systems which have 3 conserved quantities. So we convert them into 3 equations of motion. We are actually working in a coarse-grained picture where we try to look at averaging. We try to look at average description. Either we do an ensemble average, space average, sum average. So we're looking at the coarse-grained description. And by converting 2n equations into 3 equations of motion, we finally get at Euler equations of motion. And this is hydrodynamics. So Euler equations are basically PDEs, but PDEs are generally notoriously difficult to solve and especially analytically. So what we look at is it under certain circumstances, we can convert those PDEs to ODEs. So that's what we are going to see how that is done. And that leads to a scaling solution. And that leads to an exact, and we come across the TVNS solution. So this is the flow chart. So Euler equations in d dimensions are given in terms of 3 conserved fields: the density field, the velocity, the momentum field, and the energy field, which are basically depending on the corresponding conserved fields. The conserved quantities are the number of particles, the total momentum, and total energy. So we have the 3 fields. So there's a P is a pressure here. So P pressure is related to the conserved fields through the equation of state. So we consider the ideal gas equation of state, and this is in d dimensions. So we are considering a general case of d dimensions, but we can always reduce them because of the spherical symmetry of the problem. You can convert them into 3 radial coordinates, into the radial, write the 3 differential equations in terms of the radial coordinates. Now our job is to solve these 3 equations, PDEs. So now, as I said, it's very difficult to solve PDEs. So we try to go and solve ODEs. So how do we do that ODEs is that under certain cases, which is basically that depends on the initial conditions. These initial conditions are called blast wave initial condition. You give a little blast to the center of the system, you evolve the system, and then you see that under such circumstances, these PDEs can be converted to ODEs. So what happens to the system basically is that when you give an energy somewhere in the middle of the system, it leads to the formation of shock waves in the system. When the shock wave comes, it propagates in the system. Dimensional analysis gives us that the position of the shock front is given in terms of E, the total energy of the system. The rho infinity is nothing but the density of the background in the sense the region where energy is not given initially. And A is a dimensionless parameter which you have to determine. So basically the position of the shock front is given in terms of E, T, time, the rho infinity, and the dimension of the system, which is there in the D. So this leads to the shock, because there's a shock propagation, it leads to a self-similar solution in the time. So the shock propagates and is self-similar in time. And it turns out the conserved fields also depends on the position of the shock front. And we get rho, V, and E is the energy, but instead of energy, we are using the temperature. We see that we also say that they also depend on the position of the shock front through this way. And by dimensional analysis, we can, it is pretty easy to see that R by T, V can only depend on R by T. R is a radius of position of the shock front. And G, V, and Z here are the scaling functions, the dimensionless scaling functions. So this you get straightforward from a dimensional analysis. We say that. So now what we have to do is solve this. The reason we are doing all this is basically to convert these PDEs to ODEs. So finally, what we do is we put these 3 equations into the Euler equations, and finally we get the ODEs. So what happens, what we are basically doing is that this is a scaling solution. So what happens is that we have an energy, which is a Gaussian initially, and this leads to the evolution of the system. So instead of, if you solve PDEs, we keep on getting evolution and we solve it subsequent times, but we are not doing that. What we are doing is we have a scaling solution. So once you find out the scaling solution, all you need to do is stretch and compress, stretch, and we do all kinds of things topology allows us to do. So what we do is some kind of stretching and squeezing at its subsequent times, and that gives us the solution at subsequent times. So our job is basically now, once you find the solutions, once you find the scaling solution, you just, everything else is straightforward. That is how I'm saying that the PDEs are thus converted to ODEs. So the ODEs here are now that they are not dependent on X or T separately, but they're only dependent on the scaling parameter zeta, which is R by R. And 0 corresponds, zeta value 0 corresponds to the position of the core of the blast, and 1 is the corresponds to the position of the shock front. So this is how we finally convert the PDEs to ODEs. So the three Euler equations that we have here, by substituting the scaling solutions, we reduce them to 3 ODEs. So that part is solved now. Now this depends on only L. L is nothing but zeta. So these equations are now only dependent on the scaling function, the scaling variable. Now we solve the ODEs and we are done. But in order to solve the ODEs, we also, as you know, we also need a starting point. You need a point. From there, you can reconstruct the solution. And this is given by the Rankine-Hugoniot conditions, which determine the value of the scaling functions at the position of the shock front. So basically what we are doing is, instead of solving the evolution individually, completely, what we are doing is, we just solve it at one time, at a long enough time, and you just scale that. That will give the evolution at subsequent time. That's what we are doing. So that's why what we are doing is, instead of solving the evolution, we are only solving for the scaling function. That is why we are saying that we are converting the PDE to ODE. So this is a starting point of this, and this has actually turns out has been done before. And this was done in 3 dimensions, and this was done during the World War II by Taylor, John von Neumann, and Sedow. And they tried to compute the energy of the blast in the Trinity atomic explosion. And you can see this here, that initially they're giving it the self-similar propagation of energy at different time scales. And we see that there is some self-similarity, and also at much longer time scales, actually we see the shock front, there's a sharp hemispherical, there's a shock front here. So this was already been done in 3 dimensions. But now what we try to do is do the same in 1 dimension. In 1 dimension, the reason we are doing it in 1 dimension is because eventually we have to look for this solution in a microscopic system in 1 dimension. So that is why we are doing it in 1 dimension. First we solve these 3 ODEs. First thing what we did was we solved these 3 ODEs for these 3 initial conditions, and we get the solution. The solution is finally G, V, and Z in terms of zeta, but this is not explicit solution, so it's an implicit solution. We found this, and we also found the value of A. Remember I said that the position of the shock front depends on 3 parameters, only E, T, and rho infinity, but A is a dimensionless dimensionless parameter, and you have to determine that. So we also have determined the value of A. So finally we get the complete TVNS solution in 1 dimension. So this part is the first part of our talk. Now the next part is to find this out in a molecular dynamics simulation in a 1-dimensional system. And the system, as I said, must be non-integrable. If the system is integrable, it has macroscopic number of conserved quantities. So we only want 3 conserved quantities, because we are using, we have to describe it by 3 Euler equations. Each Euler equation describes the evolution of a conserved field. So we need 3 conserved quantities. So we took a non-integrable system, and the simplest non-integrable system that we can consider is the alternate mass hard particle gas in 1 dimension, M1, M2, M1, M2 aligned, and they collide elastically. If M1 is equal to M2, then as you know, it becomes an integrable system, because the velocity is just exchange of velocities. This formula, you can see that it leads to exchange of velocities, and there's nothing in that. So we take the alternate mass system, and we initially excite the system to a blast wave initial condition, where we give a Gaussian in the system, Gaussian energy distribution in the system, and we do a coarse-grained. We again look at in coarse-grained sense. We look at the evolution of conserved fields, and what we get is 0 is the core here. So we have 3 fields: density, velocity, and temperature field. 0 is the core. So once you give a Gaussian temperature here, we see that how it is propagating in time. And we see that actually it's also scaled. So once you find a solution at a given time, you can just scale and squeeze and do these kind of things. So that is why we see that actually the scaling we can see in the plots in the 3 things. And the black dotted line is nothing but the TVNS solution that we computed before. We see that there's a very good agreement between the TVNS solution and the dotted line and the scale solution, except near the core of the blast. In the core of the blast, the TVNS solution predicts a divergence of density field and the temperature field. But what we observe is there's no such divergence. So what we say is that Euler equation is not the perfect description of the evolution of conserved field in our system. So, but it's almost Euler equation because the agreement is very good everywhere. So we add some terms to the Euler equations, and this becomes the Navier-Stokes-Fourier equation. So this is the three equations which we consider. Note that the three equations on the left, if you discard the part on the right hand side, the three is nothing but these three are Euler equations written in a different form. We just added some few terms, two terms. The first term, this is the Navier-Stokes term, which has the viscosity. And the second part is the conductivity, which has the conductivity. This is the Fourier term. So because of these two terms, this becomes a Navier-Stokes-Fourier equation. Now, if we try to evolve this system, this set of equations from a Gaussian initial condition, we do this with the McCormack method, we find the same thing. We find a very good agreement. We find the evolution near the core, and we see that the scaling happens. And it turns out that as in the same case with the microscopic simulations, there's no the agreement fails only near the core of the blast in the density and the temperature profiles. But the thing to note that is that the Navier-Stokes-Fourier equation is a very good description of the system when compared to Euler equations. Now, which brings us to the question, why is it failing? Why are the Euler equations failing? The last part of the talk. And that is because in the Euler equation, the difference between Navier-Stokes-Fourier and Euler equation is these terms. It turns out that specifically this conductivity term contributes. It contributes not everywhere. It only contributes near the core of the blast, which is why we are getting this disagreement. So basically what happens is that another way of putting this is that TVNS scaling is not applicable near the core of the blast. That is because if you consider the TVNS scaling, the TVNS scaling actually predicts that the dissipation term scale as t power minus 1/3. If they scale as t power minus 1/3 in the long-term limit, they should not contribute. But they are contributing. It means that TVNS scaling is not valid near the core of the blast. And what you have to do is you have to look for some other scaling. So the core scaling, it turns out, is not the TVNS scaling, but you get a very weird exponent, x goes as t power 38/93. And we see that we get a different exponents, t power minus 4/31 in the density profile. The velocity profile is different, t is different. And this is a core scaling. And this is in contrast to the TVNS scaling. The TVNS scaling profile, you get something like this. The TVNS scaling profile, you get t power minus 1/3 and t power minus 2/3 here. These are basically how do you scale the x-axis and y-axis to get that. These things we are getting different near the core and near the TV and near the other areas. So I like to conclude the talk by talking about basically what you have done. The basic question that we try to address is how do conserved fields evolve in a macroscopic system? That's what in a macroscopic Hamiltonian system. And for that, we try to describe it in terms of conserved fields, which are the slow degrees of freedom. So instead of describing each and every particle, you only talk about the slowly varying fields. And these are the conserved fields. That's why we enter the realm of hydrodynamics. And in hydrodynamics, we talk about Euler equations. And in these Euler equations, we have a TVNS scaling solution for blast wave initial conditions. And we see that the TVNS solution is observed for the alternate mass hard particle gas in our system. And the agreement is very good everywhere, except near the core of the blast. And the core of the blast, there is a disagreement because the contribution of the conductivity term. And this is not accounted by Euler equation. In Euler equation, there is no conductivity term. Therefore, we consider the Navier-Stokes-Fourier equation, which has the conductivity term. And we find a very good agreement. Thank you. Any questions? Yeah.
Hello?
Yes.
So where is the self-similarity here?
Yeah.
You mentioned some self.
Yeah, that's a self-similarity in time. So basically what we are saying is that instead of solving the evolution at different times, once we solve at a given time, then you apply self-similarity. So at subsequent times, you don't have to solve it separately. Once you have it at a given time, you just scale the x-axis and y-axis accordingly, and that gives a solution. That is what I mean self-similarity.
But then is there like a conformal symmetry?
So initially we give the initial condition, the symmetry, whatever symmetry we give the initial condition, we give a Gaussian in the initial, so that will be maintained throughout. So there's no symmetry problem here.
Okay, thank you.
Hi, Santhosh. Hi. So in the expression of R, like it's independent of the microscopic model, is it?
Yeah, yeah, I see your point.
And even the scaling functions and all that.
Yeah, now please tell me what's your question in R.
Yeah, this is independent of microscopic model.
It only depends on the dimension. It is independent of the microscopic.
So A, you showed from Euler's equation, there's some prediction for A.
Yeah.
That turns out to be true even from the microscopic model that you considered. Okay. Where exactly is the information of which model you are considering in the hydrodynamics?
There is no, so the hydrodynamics, what we try to say is that there's no, that's a good question. So in the hydrodynamics, it doesn't depend on the model you take, as long as it is there's an ideal gas equation of state. So because the pressure has to relate to conserved fields, so we only take alternate mass hard particle gas where the collision is only through elastic collision and all when we take ideal gas equation of state. However, if the equation of state is slightly different, let's say the particles are connected by springs and we try to do the FPU chain or something like that, there the equation of state is not the same as ideal gas equation of state. Therefore, it will be different. So long as the equation of state is ideal gas equation of state, then there will be the same for everything.
Thank you.
Yeah, am I audible? Yeah. So in this shock wave wavefront equation, shouldn't at large times the wavefront at least propagate ballistically, like linearly with time?
So by the thing is that that depends on the initial condition what we give. So we have explicitly mentioned we given a blast wave initial condition, and in fact it can be derived that for a blast wave initial condition the propagation is not ballistic and it is sub-ballistic. It is x by t power 2/3. There are some initial conditions, however, that if you give them, and that will lead to a ballistic propagation.
So this one is sub-ballistic in all dimensions.
This one is x goes as r goes as t power 2 by 2 plus d, so it goes as sub-ballistic in all the dimensions. Thank you.
Yeah, thank you, Santhosh.